Thank you. Congratulations to Mordecai for pronouncing my surname. Okay, so the project that I'm going to speak about today is a collaboration between our group in Munich, including Till Binstiel and Sebastian Stamner, who are both here, and also the Shengtai Li and Hui Li at Los Alamos National Laboratory, who provide the hydrodynamic part and also the computational resources. And those results are not yet public, are not yet even submitted, and I'm pretty sure I would be submitting this paper right now if I didn't have to travel to all these conferences. But I thought it would be nice to start with this like classic Doulemont plot, and since no one showed that at this conference yet, and this is like a must-have for every planet formation conference, I think. And this is just to remind you that if we want to build planets using, like starting with the smallest solids that we think we have available in the protoplanetary disk, which is the submicron and micron-sized grains, then the road to forming Earth-sized planet is already very long, because we would need to go through about 40 orders of magnitude in mass to make just one Earth, which means we would need to bring together 10 to the 40 of these micron-sized grains to build one Earth-sized planet. And I guess this is one of the reasons that n-body codes would rather start somewhere here and then go ahead and build a planet. Actually for Earth, this is not the worst, right? Because we don't really have such a strict time limit to form Earth. Like we can take like 100 mega years or something. But if we think about Jupiter, then it gets much worse, because we have to form the core of Jupiter, which is like about 10 times the Earth, in time before the gas disk disperses. And we think this is only a couple of million years. But in this talk, I'm not really going through all the stages of planet formation. I'm going to focus on the very early stages, when the micron-sized grains would grow to form the famous pebbles that we can then use to form planetesimals and to grow these planetesimals to cores. And as you may get from previous talks, especially yesterday, dust coagulation is actually very important, not only for building planets, but it's also important for many different things. And particularly, dust is actually the thing we are observing now with ALMA, and it also influences the opacities, it determines the temperature structure, the ionization and chemistry, and many different things. So if you are, hopefully you are now convinced that you should be actually thinking and including dust coagulation in your models. And I summarized here the two possible ways that you could use to include dust coagulation. And one way is to treat dust as particles, and then to solve for collisions, because I already told you we need like something like 10 to the 40 of those particles, so probably that's not feasible. We need to usually go to some kind of representative particle approach and then to solve for collisions. So for the thing that drives the growth of particles, we would need something like Monte Carlo models. And I was developing one of those models based on Jaume and Doulemont method from 2008, but there are also different codes for that, especially the Banjan here had very recently a paper with completely new implementation of this kind of approach. Or we can treat dust as fluid, and then to solve for dust coagulation, we need to include the mass grid, right? And we need to shift the masses, the density of dust in between different mass bins. And the way to know how much of the dust you need to shift is to solve the Smoluchowski equation, which here is just in its simplest form, only dependent on mass and only including collisions that lead to sticking. And there are also quite a few codes, quite a few people were working in this approach. And if you want to know more, I wrote a paper in 2014 during my PhD that pretty much compares the two methods and has very extensive list of limitations of each of those methods, because they of course, no method is perfect, right? And they just have very different problems. And before you choose what you want to use, you should be aware of this. Okay, so anyway, never mind which method you choose. The results that you get in case of what we have been usually doing, which was azimutally averaged and vertically averaged approach and a smooth disk, so like some kind of minimum mass solar nebula like power law disk, will be very similar. And we usually show the results of dust coagulation simulations using this kind of plot, where on x-axis we have distance to the central star, which would be somewhere here, right? So we have 1 AU, 10 AU, 100 AU. And then on y-axis, we have particle size. And we will be starting here with all the dust just in micron size. And then I plotted, so color-coded will be dust density corresponding to given size at given orbital distance. And I plotted here 2 lines, which will correspond to our predictions on the limits of the growth. So there are 2 major problems. One is fragmentation barrier, which basically has to do with the fact that the larger the dust grain grow, the more, the faster the collisions become. And from laboratory experiments, we expect that there is some sort of maximum impact velocity for which the collisions cannot lead to sticking anymore. And for here, I assume this is 10 meters per second. And then we have the second problem, which is the drift barrier, which has to do with this radial drift thing, that the larger the particle grows, the faster it will move inwards in the disk. And there is, again, some critical size for which the drift timescale will become shorter than the growth timescale. Okay, so now let's play this simulation. What you see is that the dust growth proceeds kind of inside out. So at the beginning, we grow very fast in the inner disk. And then what happens is that this grain that starts to grow in the inner disk, they quickly reach the fragmentation limit, right? And in the outer part of the disk is actually the drift barrier that is more important. And then what happens is that this dust will just be removed, right? And our dust is gone in just about 1 million years. So it's actually gone from our smooth disk faster than the gas is gone. And I just want to mention that this animation is done using the DustPy code that Sebastian and Tila are developing, which is a Python-based version of the code that the community was using before, which was Fortran. And Sebastian promised everyone that this code goes public 21st of June this year. So let's keep his word, and feel free to write him reminders if you are interested, because he needs some pressure on this one. Okay, so anyway, this was our smooth disk. This is our kind of a benchmark test, benchmark case, right, that we are usually using. But the main problem here is that we don't have really any dust growth past these 3 centimeter sizes, and also our dust population, like all our dust, is gone in 1 million years, right? So, and there is no way to do any planets here. So how do planets form? We don't know, but we kind of suspect that this has something to do with the fact that the disks are not smooth, and that there are many ways to generate some kind of pressure bumps. And if you don't have a planet yet, which is like a preferred way to induce a pressure bump, then you would have to go for some hydro or MHD instabilities. But this is something we cannot really model, right, in this code. So we have to now go to hydrodynamic. And including dust growth in hydrodynamic models is not easy. Probably no one knows that, but this was my master project back in 2010, to include Monte Carlo version, so this representative particle Monte Carlo version in MHD code that was developed in Toruń, Poland, which is called Piernik. It's also a public code. And this master project kind of failed, right? Because it's really hard, and especially for a master student. So now we are trying again. And a typical way to approach dust in hydrodynamic simulations is that you have a second fluid, right? On top of gas, you also have dust that has slightly different behavior because it's a pressureless fluid. But then you have to assume something about the size. And typically, you just have one dust fluid, and you assume that is as some size or some fixed Stokes number, and you just keep it fixed for your simulation. But this is not what we kind of want for dust coagulation. So we need more of these dust fluids. And as especially Martin pointed out, we need a lot of dust fluids. And here for coagulation, this will be similar numbers. So for the results I will show you later, we used 151 dust fluids, which kind of gives us a good resolution in this mass grid. And a new thing that we introduce is that we can now shift mass between the dust fluids, right? So as I told you, we need to solve Smoluchowski equation that will tell us how much mass we need to transfer between different size bins to account for coagulation and fragmentation. And this is all, as you may guess, implemented in this LA Compass code suite, which is developed in Los Alamos, so it's unfortunately not a publicly available code. But maybe it will be, we will see. And then as a test case, because, so of course we tested our smooth disk approach, we haven't found anything surprising there. If you start with a smooth disk, you don't introduce, it's just a hydro simulation, you don't introduce any instability, you recover exactly the result that I showed you in, from the dust by code. So you lose all your dust, you cannot grow past 3 centimeters. So now we did something, we wanted to do something more interesting, and particularly something that possibly introduces some asymmetry. Then we just put a giant planet in, like a Jupiter, into a minimum mass solar nebula model. This is also a viscous disk, so it's, we assume alpha of 10 to minus 3 for the results that I show you here. Yesterday, Till showed you an inviscid disk case, in which case you have a giant vortex triggered just outside of the planet orbit. Okay, so now what we see here is the gas density and everything as expected, right? The planet opens a gap, you have the spiral density waves and so on. And this is gas. Now let's look at dust. We also see kind of as expected that the dust is gathering in this pressure bump outside of the planet orbit. Some of the dust is also trapped in the co-orbital region, and you see clearly that these spiral wakes are also showing in the dust. But now the cool thing is that we don't just have one dust density at each kind of grid cell of our code. What we have is the whole size distribution, right? So we can look inside of every grid cell and we can see what is the size distribution that we have there, while we take into account the coupled effect of dust coagulation and fragmentation, and at the same time the advection, which is done size by on the size by size basis. So we kind of solve hydrodynamics for all our dust fluids, but after every hydro time step, we also shift mass between different sizes. So it's kind of a fully, we also have back reaction, it's all fully coupled. So now when we look inside, when we look at this kind of pressure trap region, we kind of recover what we expect, which is coagulation fragmentation equilibrium, which basically means that the dust can grow, but there is this kind of a critical size above which the velocities are too fast, so it fragments and kind of returns small grains that regrow, and we can almost prescribe this as a power law. Then we can also look at some other regions further away from the planet, and since this was at a pretty early stage of the simulation, the dust here didn't manage yet to grow to until the fragmentation barrier, so our size distribution looks a little bit different. And now for more interesting things, we can now test how good was our previous assumption about that the disk is axisymmetric, right? Because we can now compare the dust size distribution at every like azimuthal angle, right? At every point around the same at the same distance from the star. And we actually were pretty disappointed to find that in this viscous disk, we don't really have a huge asymmetry. So the gray lines would be the different size distribution, and the red one is the averaged one, and you don't really see that much variation. And the most variation that you can see is, of course, in the planet's orbital region, right? Because the planet is at only one spot. It has some gas and dust trapped around it. There is also some trapping in the Lagrange points. And then typically, dust size kind of follows the density. So in the dense regions, you can kind of you have more dust, and it goes to a slightly larger sizes than in the places where you have low gas and dust density. Okay, and also what you could figure is that like a comparison between this and this distribution is that here you grow to much larger sizes. And this is correct. As I said, it's much easier to grow in dense regions. And now what we can also do, we can compare the results that we have with this full coagulation approach to things that have been done before, because there are too many papers to reproduce all of them now with the full coagulation approach. So we can kind of try to have some general rules and came up with some like generally what would be different, right, between the fixed size approach and with our full coagulation method. So particularly in the planet case, there was this well-known sequence that small grains can kind of follow gas and they don't open such a deep gap, but then the larger the grains are, the wider and deeper the gap gets, and the more trapping you have. And now when we compare this to like a summed up density in the full coagulation model, then you find much more like smooth gradients. And you can understand this much better if we now look at a kind of a comparison between azimutally averaged density plots, when here will be this sequence of fixed size simulations that the fluids were not interacting, right? And here we have this full coagulation simulation, and I split this total density now into different size bins that are corresponding to the ones that I used for fixed size models. And it doesn't look really bad, right? It doesn't look that different for fixed size models, because the general behavior is reproduced, that we only have the largest grains in this region of the trap. And inside of the gap, we only have the smallest grains, so it's the same. But I would like to point you to two differences. And one would be just outside, so in this trap region now. In the fixed size case, the smallest grains were just following what the gas is doing, right? So you wouldn't expect any trapping for your small grains that are completely coupled to the gas. However, if you look at the full coagulation simulations, you see that there is this bump also in the smallest dust grains. And this is because of this coupling, right? That the fluids exchange mass all the time. And since the largest grains here will fragment all the time to produce smallest grains, we also would expect, like if the fragmentation really operates, we would expect to also see trapping for the smallest grains. And another difference is that in the fixed size approach, we would only expect that grains smaller than 1 millimeter could pass through the gap. And in the full coagulation model, we find also centimeter-sized and larger grains interior to the planet. And this is because the small dust that is able to pass through the gap will also regrow and like will again produce these large grains. And to model this kind of how the dust coagulation around the planet would proceed. Previously, we were using the 1D models, so we were kind of extracting the gas evolution from hydro models, where you put a planet into a gas, and then you average the result, and you just model dust using the 1D approach. And now we are able to compare how good this was. And you see that there is quite a large difference between the 1D and 2D coagulation approach. And particularly the 1D model expects more trapping, more narrow dust density trap, and expects kind of more filled gap than our full results now. And this is connected to many things, but also to the fact that the dust grows to larger sizes in these 1D models than in 2D. And this is connected again to these 2D spiral wakes that induce more of these velocities that lead to fragmentation. And I'm going to have to speed up because I'm running out of time. So what can you do better? Are there any cheaper ways of including dust coagulation, but good at the same time? And 1D, going to kind of back to 1D is one way, but then you cannot have any asymmetric cases, right? Yeah. So what we have done, what I was already working on back in Zurich with the student Thomas Stampfel, and this work is published in 2018, was to use some kind of approach based on work of Till Birnstiel that was done for smooth 1D disks, where you use the available information about your gas disk, and you come back to having a limited number, so maybe 1 or 2 dust fluids, and you try to guess what would be the outcome of dust coagulation. You don't solve dust coagulation, but you try to guess at every grid cell what would be the size of dust using this information that you have, right? And how good is that method? So when we were writing this paper, obviously we couldn't benchmark to anything. We just said, okay, if we do this, this is what we get in the 2D case, because we didn't have the full 2D coagulation results. But now we can compare, and I think it's surprisingly good, because the red line is now this 2D simulation with this just one dust fluid and with a very simple coagulation prescription. And red line is again our full coagulation result. And you see that in the density, it matches the full results better than the 1D approach did, right? And in the sizes, you only see this major difference here. And this is actually caused by these spiral wakes again, because the simple method, it takes into account what is the local pressure gradient that will induce the drift and also will induce the collisions. But it doesn't see that this pressure gradient is very short lasting, right? As the waves are kind of sweeping through the disk. And the full coagulation, in the full coagulation, what happens is that you also have diffusion. So if you fragment it a lot in one time step, you can still replenish these large grains in the next time step by diffusion. And this is what the simple coagulation cannot do. And now the computational slide, how expensive is exactly including dust coagulation. So the simple method is basically as expensive as just doing single fluid, so fixed size single fluid, which for LA Compass, for the Los Alamos cluster on which I am running, which has 36 cores per node, is something like 124 CPU hours, which in real life is 13 minutes on a kind of small size simulation or relatively small size simulation for Los Alamos standards. Full coagulation is about 214 times more expensive. And I think this makes sense because you include 150 dust fluids instead of one dust fluid. And on top of that, you have this extra step of solving the Smoluchowski equation, right? So then on for a moderate type of sized simulation, you need to wait something like 12 hours for 1,000 orbits of the planet, I forgot to say, sorry. So this is still not bad if you can actually get all these cores. And then for the 1D approach, the dust by code, which is not MPE parallel, right? It's only OpenMP. it takes about 20 hours on 16 cores, but I think it doesn't scale super well. So probably if I run this on one core, it would be less CPU hours. Okay, so that is pretty much it, and I will just leave you with my conclusions, and I'm super happy to answer your questions.
Thank you.
I have a question regarding the steady state of your simulation, because you have coagulation fragmentation. So how can we imagine whether this is steady state or where you stop the simulation and how it evolves?
Okay, thank you for listening to this talk second time. So steady state, so the dust population, the dust size distribution, whether it's steady state or not, will depend on whether you are able to keep the density at kind of the same. So as long as you can replenish all the dust that you have lost, right, then you can imagine that this size distribution stays the same. But here, the whole simulation was done only until 4,000 orbits, right? Because 12 hours per 1,000 orbits and so on. So I think we cannot really claim that we can say something. And you kind of, for dust simulations, you don't really expect steady state, because at some point the dust will all be gone, right? You don't have unlimited reservoir of the mass.
Rosanna, did you have a question too?
So,
yeah.
So I have a quick question about your 1D versus 2D comparison. Do you mind going back to that slide?
Sure.
It might have been something that I missed. So just looking at the left-hand side, and maybe it's also there on the right as well, but you see the peak in the 1D just slightly inwards of the 2D, and I'm just wondering what...
You mean here?
Yes, exactly.
Yeah.
Just wondering if you could, were the pressure maxima at different locations? Or,
exactly this. This is exactly the case, that if you look at 2D, the planet is at only one place at one time, right? And then the 1D kind of averages it out, and it sees only one pressure maximum, right, at one radial location. So this is one reason for which in 2D this trap is kind of smeared out. And another reason is that we think the spiral wakes also kind of introduce some more of a mixing, and the 1D method is just not able to see that.
Thank you.
Simeon?
Right, so these are all 2D models. So what are you assuming about the vertical distribution of all the particles?
So we assume the standard vertically integrated kind of model, for which every dust size has a Gaussian distribution that corresponds to its Stokes number. So like the larger grains are more settled to the midplane. But of course, yeah, it's... yeah, that's a good question. We can, because we were cheating, and for dust we actually put some alpha. So only for gas we didn't.
Excellent talk. Thanks. I was wondering about the overhead compared to pure hydro. So the last slide you mentioned it, but the resolution is missing. So
the resolution of the models?
Yeah.
It was 1024 in every direction.
1024?
Yeah, 1024 in both in R and in phi.
Using both hydro and the dust. So the overhead, I mean, if you ran only hydro, like how long would these models take?
Yeah, this is a good question. I can check that maybe later. I'm not sure if I have any pure hydro simulation though. Yeah.
Any other question? Kathy?
Compare the single dust particles with the coagulation model. It looks as though you're not really changing the location of the maximum very much. I'm just thinking about the way that the location of the dust maximum is used as a sort of way to weigh planets, and that's usually done by groups who put in just a bunch of different Stokes numbers. Am I right that you're not really, you wouldn't get vastly the wrong answer by not including coagulation?
So in this like green line here, the coagulation is kind of included, right? Because we
Okay,
look.
so I wasn't thinking. I was actually thinking of your
Ah,
comparison with the
okay.
single, the
Yeah,
single
and
things,
the
which
blue
is what
one.
people
This
tend.
one, you
Yeah,
mean.
people tend to run those kinds of models and figure out
Yes.
the dust maximum from that. It looks like it's roughly in the same place, but I'm not very good at.
It is roughly in the
eyeballing.
same place,
Yeah.
but so if you sum up all these sizes, then it depends what you assumed for the overall size distribution, right?
Yeah.
And here I assumed like that it's MRN distribution. So it's, and it kind of also very much depends on what you assume for your maximum size. And there is actually no way of knowing what your maximum size would be if you don't do some kind of coagulation estimate before. So I think it's still worth to kind of do some estimate, at least simple one, to at least know what would be this maximum size. Because most of the mass in MRN distribution will be in this maximum size.
Okay, thank you again.